So we are approaching the final stages of this introduction to FIM course. And I'll tell you what I'm going to do. In the next 2 lectures, what I'm going to aim for is to do the formal framework for probability theory and stochastic analysis. We have run into stochastic processes and probability issues a lot in this course. I have so far treated them building on what you already know and building on your intuition. What I'm going to do now is I'm going to slowly crawl our way back into the formalism, which is how mathematicians do this. And that will end tomorrow in our class tomorrow. I'm going to take the benefit of the fact that we've already seen enough of those examples so that when these formal structures come up, we understand them intuitively and from a practical perspective. Okay, so that's what I will do. The reason to do that is there are, as topics get sophisticated, and very likely some of your other courses in this program, you're going to run into more sophisticated descriptions of financial realities that will require more advanced considerations as to what these mathematical objects are. And this is the objective that I will do. I don't think you're going to learn very much between today and tomorrow. You will learn maybe a little bit. What we aim to get between this lecture and the next one is a formal understanding of how these intricate objects are handled, but also to get a historical overview of one of the greatest accomplishments of mathematics in the 20th century. The fact that dealing with the unknown was doable is something that presented itself towards the end of the 19th century. And it became one of the very famous Hilbert problems, which was presumed to be one of the most difficult ones. If you know something about mathematics, you would see that, for example, the Riemann hypothesis was presented as one of the challenges for the 20th century. And this one, the formalization of essentially probability theory, was considered to be more difficult. Turns out that was not the case. In fact, it took only a few years for the main developments to actually happen. So it has been a very interesting evolution in the 20th century, and we're going to take advantage of that today. So I'm going to do a math today and tomorrow in the next two lectures, and that should be enough. I think that will suffice for us to understand that. And we will use the rear view mirror to look at everything we have done and maybe look at it from a new light. That's the objective for the lectures today and tomorrow. Then the last one, the one that we'll do on Monday, is going to be somehow back to reality, assuming that today is not reality, back to reality. And then I will just end my course with a review of some of the most modern topics in finance that we'll be dealing with. I'll talk about some aspects of asset management. I'll talk about a little bit of sustainability and somehow where this sector is going. Okay, so that's the plan for the next, for the last 3 lectures which remain in this course. All right. So I'm going to make a statement and also somehow a preview of the other course I'll be teaching in this program, which is the course on machine learning. When you look at data science, I like to view data science from 2 perspectives. One is what I will be calling today dynamic data science, which is the modern terminology for stochastic processes, and making a distinction between computer data science. In dynamic data science, this is going to be driven by mathematical models, hence the emphasis today and tomorrow on the mathematics. These are mathematical models, the advantage of which is that they exist in our mind only. So we have complete control over them. When you look at computer models, which will be the topic of my other course in this program, the course on data science, those models live on computers, so they are not within our reach. That is a fundamental difference between what we're doing today and what we'll be doing in the spring in my course in data science. The computers then will be in charge. We just hope to understand something. But here we are in charge. The mathematical models live inside us, so we understand that. When it comes to the applicability of what we're doing today, model is, we have to pick a model. And picking a model means that we can make a mistake. Because of that, we're going to try to learn how the different models achieve different things. When we move to the computer side of things, the model risk that we face when we pick a model will be replaced by another problem, which is the data overfitting problem. So that's the computer's version of our challenge to come up with the right model. We will see that in the data science aspect, things are perhaps hard to formulate. We're going to have to create mathematical objects with lots of strange symbols and lots of Greek letters, okay? But they're very easy to implement because, again, we are in complete control of what's happening. When we move to the computational side of things, things will be very easy to formulate, but they are difficult to implement because the computer is the one who will have to do all the heavy lifting. And again, we're not in charge of the computer world. With AI, these things become easier because somehow the computers take care of it themselves. So AI will make that the implementation difficulties will be still difficult, but handled by the computers, not by humans. Okay. The other advantage that I see in dynamic data science is that it provides a philosophical framework. So we can talk about processes which are geometric brownian motion or mean reverting or things like that, things that have meaning. Whereas when you look at computational data science, we oftentimes will not know what's going on. The computers just find the path to the solution, and we will be done with that. In the data science that I will do today, we will learn from it, but in the when we apply this with computers, we simply just solve problems. That's all we will do. Okay, so some history for what I'm doing. I told you that this has been one of the great accomplishments of the 20th century. And I'm going to start something which I already mentioned, but it makes sense to repeat here. Brownian motion is a very interesting topic because it bears the name of someone that had not very much to do with the actual development of the theory of the Brownian motion, but he's the one who first started to use the term about this type of motion, which is erratic and something that everybody knew would not be possible to understand with the Newtonian mechanics, which was the mechanics available at the time. So Robert Brown was a botanist in the early 19th century, okay? And he first talked about this in the year 1827 when he was talking about the motions of particles suspended in fluid, liquid or gas. And he noted that this motion is characterized by regular random movements of particles. And in the book, The Origin of the Species, published in 1859, Darwin mentioned the work of Brown as he was talking about the movement of small particles within plant cells. In his evolutionary biology description, he mentioned the work of Robert Brown, and perhaps this is part of the reason why we still use that name today. And we had a chance to review Einstein's theory. In fact, I showed you that Einstein's theory was a way to understand Randomness from a differential equations perspective, and we saw the similarities between that and the Black-Scholes theory that we developed shortly after. So all of these are things that we have seen, and all of that fits into that wonderful development that happened in the 19th century going into the 20th century. Okay? And Einstein used that to provide evidence for the existence of atoms and molecules. So we went from plants, evolutionary biology, atoms and molecules, then finance. So today and tomorrow I'm here to give you the framework, the mathematical framework, to unify all of that. That's what I will be doing today. And we've already used that in the derivation of the stock price process, and today I'm going to be discussing this again in a mathematical framework. Much of what I will do today we've already seen, but today I will heighten the mathematical treatment of that, and that will be heightened even further tomorrow when I give you the construction of stochastic processes in all of its mathematical glory. Okay, all right. So a technical definition: a continuous time process. Brownian motion will be a continuous time stochastic process, which I have defined. I'll define that tomorrow. Okay, I'm not going to define that today. We have an understanding of what a stochastic process is. I'll define that. I'll give you a mathematical definition tomorrow. But Brownian motion will be a continuous time process, which is sometimes written as dW, as we did or a dB, if you want to pay homage to Brown, who's the one who first invented it, or Wiener, Norbert Wiener, who's the one who formalized it. So this is interesting because Brown in 1827 is the one who first started to talk about that. There's nothing he can do. And then Wiener, Norbert Wiener, 100 years later, was the one that formalized that. And it's interesting that mathematicians today use B for Brown or W for Wiener interchangeably. But there's a historical reason for that. That goes back 100 years to Wiener and 200 years to Brown. Okay, exactly, almost exactly 1 and 200 years. Interesting. All right, so typically what I like to do, I sometimes run out of variable names, so I call them dW, dz, dB, or something like that. But when something that I've noticed is when you're doing something which is more rigorous, more mathematical, more fundamental, you write dW, and we're going to do a lot of that today. And when you want to do something more intuitive, people tend to write dB, but that's just the terminology. Okay, so here's the definition. And I'm getting deeper and deeper into definitions. So WT is a stochastic process. Footnote, I'll define a stochastic process tomorrow. Okay? But W is a stochastic process that satisfies the following properties. First, an initial condition. The value today is 0, so it starts at the origin. Then it has independent increments, which means that if you look at the distance traveled, if you look at the difference between the random variables WT1 and WT2, or WT3 and WT4, if you pick 2 or 3 or 4, but if you look at two different increments, those increments are independent of each other. Okay, so you pick any collection of points in time. I pick 3 here, and then you look at the differences between the first and the second and the third. Those are independent random variables. We'll see tomorrow that the definition of a stochastic process is essentially something. It's a function defined on the positive real line, which is time, that at every point in time gives us a random variable. I'll formalize this better tomorrow. For now, this definition will work. So if Wt is a random variable for the values of t, Wt2 minus Wt1 is the difference of two random variables, hence another random variable. These are random variables that live on different spaces, but I'll give you all of that tomorrow. That's why I don't want to be too formal today, because I can't. I haven't given you everything you need to know to understand this, but we have the intuition, so I'm going to continue to be part intuition today. And then the third and key assumption, this is perhaps the key assumption that makes Brownian motion what it is that the increments between two times are normally distributed with zero mean and variance t2 minus t1. In other words, the variance is the same as the time lapsed between the two observations. Okay, mathematically speaking, if I look at these two random variables, the difference is a normally distributed random variable with mean 0 and standard deviation t minus s. Okay. A random variable is something which is defined on a particular event space, but that will come tomorrow. I'm not going to be dealing with that today. Now, so these are the characteristics of a Brownian motion. In the theory of stochastic processes, which we'll see tomorrow, one can prove that such object exists and is unique under certain circumstances. So for us, this is good enough to continue and to do what I'm going to be doing today. Okay? So the mathematical properties and definitions I leave for tomorrow. Now, one consequence of this, things that we've already mentioned, but today I get to formalize, is sample paths are going to be continuous with probability 1, but they're going to be differentiable with probability 0. To do this, we realize that we need to have a slightly better mathematical definition of what these objects are, but that's coming tomorrow. And then we can prove the continuity and the lack of differentiability. Okay, that's in one dimension. In n dimensions, the definition of this is very similar. We're dealing with a vector now. It's not a number, it's a vector. As we will see tomorrow, these things will make no difference to us because a stochastic process is going to be something that maps the real line parameterized in time into anything, really anything, whether it's the Euclidean one-dimensional space, the Euclidean n-dimensional space, or some other space is going to be treated exactly the same. So for us, whether we go from a number to a vector is going to make not very much of a difference. Makes a difference in the applications, but not in the mathematical formalism. So this is a vector that has components, and I'm going to be assuming that the components are fixed and equal to n, and therefore finite. And then this is going to have a certain properties. The first is an initial condition, and I'm going to assume that the initial condition is that it starts at the origin of this high-dimensional Euclidean space. And it has independent increments, just like before. Before, it's actually written exactly the same way. In the previous slide, the W's were numbers. Here they are vectors. And I advance you that the W's could be some other higher dimensional objects, even living in infinite dimensions, and would still be essentially doing the same. Okay, so that's the advantage of the mathematical framework for these definitions, which it allows us to make them very general and even go to places where we have no intuition. Okay. And then the increments are random vectors, just like before, and an implication of that is because the vectors are independent as vectors, that means that the marginals must be independent too. And I highlight that the reverse is not true. If you have vectors whose marginals are independent, does not mean that the vectors are independent. So here I'm assuming that the independence is at the vector level, which trickle down to the component level. Okay? This is a common mistake, to think that if the components are independent, the vectors will be independent. That is not true. So here I'm making the strong assumption, which is that it's the vectors which are independent, not the individual components. And then not only that, but I assume that the increments are Gaussian. Gaussian with a variance-covariance matrix given by what we have here. We have the time lapsed in the diagonal and zeros outside of the diagonal. Some comments. The zeros outside of the diagonal are unavoidable because these are independent variables, so they have to be uncorrelated, therefore the correlation must be zero. And the fact that we have the time lapsed in the diagonal is exactly the same as what we assumed earlier, that the variance of my one-dimensional Brownian motion was the time lapsed. In this case is the variance for each of the components of the Brownian motion, which is the time lapsed. Okay, so this is the correct generalization of Brownian motion to finite dimensions. And I'm not going to do this, but I should say that we could generalize this to infinite dimensions not very difficultly. We would be able to do this by simply going from vectors in Euclidean space to functions in some appropriate function space. For example, L2, if you know what I'm talking about. Okay, so this is the path that we can follow or the win that we will get if we are able to define the mathematical framework for these types of objects. Okay, so I'm going to have a constant fear today and tomorrow that I could lose you in some of these things. So I'm going to take a pause here and make sure that we're all in the same page. And for those of you watching the video, maybe it's a good time to stop and make sure that everything that has been said so far is understood. This is not hard, we have seen it already. The only thing that's different, the only thing that's new is perhaps my notation or perhaps the fact that I'm talking about these objects as abstract objects without making a reference to a specific application. All good?
That's all good.
All right. So then I can continue then, and I will make some additional clarifications or maybe additional explanations of some of the objects that I'm talking about. The difference between the random variables at two observations, t and s, is normally distributed with mean zero and variance covariance matrix equal to the identity matrix times the time lapsed, t minus s. That's exactly what we said earlier, written in mathematical terms. Okay, as you can see, the mathematical symbolism is starting to pick up and it'll reach its full glory tomorrow. And this has all of the information that we need to work with these objects that we have just invented. It gives us the evolution across time and also the dependence across marginals. Okay, so there's two dimensions at work here. One is the time dimension and the other is the spatial dimension from one component to the next. Okay, so as in the case of one-dimensional Brownian motion, the theory of stochastic processes will prove that such an object exists. We are only listing its properties. The object exists, and the sample paths will be continuous with probability 1 and will be differentiable with probability 0, just as before. Okay. Now, let me now take this and move to the case of correlated Brownian motion. If I want to do correlated Brownian motion, then what we do is going to be very simple if we follow the right approach, which is we have so far assumed independence of Brownian motion across variables, okay, in different dimensions. We've done that to keep things as simple as possible, but of course we can easily mess with that relationship to get whichever correlation structure we want, and we can do this by doing linear transformations. And the reason is that Gaussian random variables, the normal distribution is closed under linear transformations. So we're going to use that to take linear transformations, apply that on our Wiener process or Brownian motion, and achieve any desired correlation between our random variables. Okay, so if we take a Brownian motion divided by WT, we take a Wiener process, vectorial Wiener process, and I multiply that by any variance-covariance matrix that I wish, call it V, the result of that is going to be a Brownian motion. It's being rotated, it's being mapped in a linear fashion by this matrix V. When I do that, we can see that the Brownian motion will have increments now which are normally distributed with still mean zero, and variance which is the time-lapse times that fixed variance-covariance matrix. So a very simple linear transformation of a Brownian motion will give me any correlation that I want. The correlation is going to move through time through a scalar multiplication of the time lapse. That I cannot change, but I can change the dependent structure in my Brownian paths. Okay. However, the independence of increments over time is a fundamental property that we cannot change. Okay, so again, we've been able to change the independence across variables that we can do through linear transformations, but we will not be able to change the independence over time. That's fundamental. We can't and we don't want to. Part of the reason that we're doing this is because these models are they're very flexible, but they retain one important characteristic, which is that they are Markovian. They have no memory. This is the important part of saying that the over time these processes have independent increments. They lack memory. We can relate this back to our experiment where we were flipping a coin. When you flip a coin now, the coin does not remember what the previous flip was. That characteristic is called the Markovian characteristic, or the lack of memory, or the fact that as you run experiments over time, the results are independent of each other. That we don't want to mess with. We also saw that if we lose that, we said very briefly, but we saw that if we lose that, then we run into a computational nightmare, because the data that we will need to run our processes is going to blow up as our problem becomes complex. So we like to keep this property. It is fundamental for us to be able to do things in a practical way. Okay, so we've been able to take Brownian motion and we've been able to change the dependent structure within our variables. We're going to be able to change the mean too, and we do that by adding what's called a drift. So far we've dealt with Brownian motion centered at the origin, but of course I can add something to it, and then the result will be a Brownian motion that has the variance-covariance matrix that we specified and a drift, which is for us to choose. I call it with the Greek letter mu. The result, if I simply add a function, this is a deterministic function, okay, not a stochastic one. If I add a deterministic function to my Brownian motion, then I see that the increments between Brownian motions is the difference between the means, or the drift, times the variance-covariance matrix chosen times the time lapsed. Okay, and now you can see I'm switching from W to B because I'm running out of variable names. Okay, so in this fashion, through linear transformation, affine transformations, multiplications by matrices, and summations of vectors, we can take the basic bare bones 0, 1 Brownian motion into a wider and wider class of stochastic processes that allow us to develop parametric models of diffusion. Okay. Now I have I've only added drifts, which are a function of time. They're not a function of space. I used a variance-covariance matrix, which is fixed. It does not change over time. Once you start to mess with that, you can generalize the class of processes even further. But we're going to be happy with this for today. Okay? Tomorrow will be a different approach. And I reiterate the fact that the lack of memory characteristic of this is important. We are not going to get rid of that. Okay? In other words, the independence of the increments over time is something we are not going to dispose of. The increments between two time intervals are independent of the increments between two other different time intervals, no matter what the choices for the time intervals are. Okay, now some properties of this object, this mathematical object, is that if I have two Brownian motions in dimension 1 and I add them up, the result is a Brownian motion 2. So this is a very convenient property. It allows me to superimpose Brownian motions, oftentimes also called white noise. It allows me to superimpose Brownian motions to come up with new Brownian motions. So that is a good way to grow the model flexibility we have when we want to model what's going on. And if they have drifts given by drift variables mu1, mu2, mu sub I, and if they had covariance matrices denoted by wi always multiplied by the square root of time, then their resulting Brownian motion will have a drift which is the sum of the drifts, so the linear combination of the drifts, and a variance covariance matrix that we can calculate explicitly and equal to that. If they are independent, if they are dependent, the solution, the result is a bit more complicated. Okay. So in the case of correlation, the result that we get for the drift is the same, is linear, but the covariance matrix now gets a bit more complicated, and it still scales like the square root of time, where we're never going to lose that. But then the variance covariance matrix that we have is the sum of the variance covariance matrices times twice the covariance between the individual Brownian paths. Okay. Now this formula is linked to one that we've seen over and over and over again. We saw it when we defined the Riesz matrix methodology, for example, which is that the sum of Brownian motions, the sum of Gaussian variables it gives rise to a new Gaussian variable. Okay, this is what is really at the heart of everything that we're talking about here. And it's very important to highlight that one key element here is the fact that the randomness governing Brownian motion is normal. And the reason is that if we lose that normality, we lose a very important relationship between independence and correlation. The Gaussian world has this feature, which is two variables which are uncorrelated are independent. Normally that's not the case. Correlation is a second moment, whereas independence is a functional statement, not just for a square function, something much stronger than correlation. Because we're in a Gaussian world, these things are particularly simple, and many of these things are true. If we leave the Gaussian world, we lose that. Okay. In fact, most often Brownian motions are not jointly Gaussian. They are generated by correlated factors, which, although they have a correlation, they're not jointly Gaussian, in which case this formula is not true, and it gives rise to some anomalies. Okay, so just important to point out. Now, Brownian motion contains some other features. It contains, for example, the scaling property, which says that if in dimension 1 I can scale time, I can change my watch, okay, and but if I change my watch, note that I need to change my amplitude too. Why? Because there's a relationship between how I grow and how much time has lapsed. If time now changes at a different pace, then my growth will have to change at a different pace too. Okay, so Brownian motion, if you change variables in time, will continue to be Brownian motion if you scale it so that it continues to have that relationship between growth and time. And this is true for any change of clocks, which is positive. Okay, it goes forward in time. All right. Another property is time inversion. You can change the clock backwards. You can walk backwards, but if you do that, the result is also Brownian motion. But then you also have to scale your amplitude, and the amplitude will have to scale in an inverse way from how you travel through time. So all these are characteristics of Brownian motion. I can give you proofs. I'm not interested in giving you proofs. I just state them for you. Okay. Now, we have successfully defined at the level of today what Brownian motion is and some of the characteristics. Some of the most important aspects of Brownian motion, and actually any stochastic process, is what's called the heating time. What is the heating time? It's something we've already seen again. I will define it for you for Brownian motion. This could be defined for any other stochastic process. So, but if I have a Brownian motion, I will pick dimension 1, which is easier. Then we define the heating time as the first time the Brownian motion hits a point x. Defined mathematically back as the heating time t sub x, of course, it's a function of x, is the first time that the Brownian motion hits that point x. Because Brownian motion is random, because it's stochastic, at every point in time we get a stochastic random variable. This t sub x is a random variable too. We don't know what it is, but there's some characteristics to that. Now, this is something we already saw. We saw this in fact yesterday, I believe. Okay, when we're looking at credit risk, I'll give you an example of this. And we had the default process. Remember, the default process was 0 until you default, and then it became 1. Remember that? We saw that yesterday. So we can think of the process of default as the heating time with x equals 1. Now, this is just vocabulary at this point. But it's more than that. It's because these heating times appear for stochastic processes in natural applications all the time. The fact that we saw it yesterday is perhaps proof, or I want to use it as validation, that what I'm talking about here is very, very important. Heating times for any stochastic process are very important. So we're going to spend a little bit of time trying to understand heating times for Brownian motion. Heating times for Brownian motion are remarkably simple. We're going to be able to obtain wonderful formulas which point to the earlier fact that I mentioned, which is the advantage of doing things mathematically as opposed to using machine learning, is that we understand things. So this is used in credit risk. We saw that earlier. It's used in market risk. It's used in investment management and this and that. In fact, I think we already saw an application in asset management before. I'm not sure, but I'm going to repeat that today, because today we're going to become so powerful with some of these techniques that we're going to be able to obtain some good consequences of what we're doing. Ruining, for example, is a straightforward concept derived from heating times. It's the time when you run out of money. That is a heating time too. So most of the things are heating times. Okay. Now, in an attempt to understand heating times, I want to bring up now a principle of Brownian motion. This applies only to Brownian motion, or maybe some other processes there, but it's something fairly specific to Brownian motion. It's called the reflection principle. It's something very intuitive, but it's going to have tremendous consequences in our ability to calculate the distribution of heating times. Okay, so the reflection principle basically tells us that the probability that Brownian motion is bigger than a certain value at a point in time, conditional that the heating time has already happened is a half. Okay? If the heating time has not happened yet, then it will be 0. But if the heating time has happened already, the probability that brownian motion is bigger than x is a half. And the intuition behind this is that for every path that reaches x, there is one that does not, because it reflects away from x. Okay, I have a picture to show this to you. It's here. So here we have, these are two paths that up until point x, and you see that point x is, I have it there at the heating time, up until point x. Once my brownian motion continues to move forward, and I have the move forward graph in black, I can reflect that path only after I hit x. I can reflect it around x, and I can see, written in or depicted in red, that if the black path is above x, the red path will be below x. So for every path that goes above x, there's one that goes below x. And that's why this probability is a half, because I have a one-to-one mapping between every event that will surpass x to another one that will be strictly less than x. So this is the reason for that reflection principle result. And okay, there we go. And I'm going to use the reflection principle to state the. I'm going to use this to understand the distribution of heating times as follows. If brownian motion starts at 0, and I give myself a certain level, which is a positive number, then the law of conditional expectations will tell me that the probability that my brownian motion exceeds the value x is equal to the probability that it exceeds the value x conditional on the heating time being before t, plus the same thing conditional that the heating time is after t, because these are two complementary events. So I can decompose the probability of one event into the conditional probability of two complementary events, multiplied by the probability of each of those events, which is here. That's the probability of the first event and probability of the second event. Okay? So this is, from elementary probability, we know that the probability of anything is going to be decomposed into the probability conditional on two independent complementary events. Now, if I analyze that further, I see that because brownian paths are continuous, if the heating time has not happened yet at time t, then B has not reached point x. It's impossible that B has reached point x if the heating time is going to happen later. Impossible. That means that the probability that brownian motion is bigger than x, conditional on Tx bigger than T, is going to be 0. And that yields the result that the probability that my brownian motion exceeding x is equal to the probability that my brownian motion exceeds x, conditional on the heating time being less than or equal to t times that probability of the heating time, which leads to, because of using the reflection principle, I get that the probability of that event, B exceeding x, conditional on the heating time being less than t is equal to a half. And that means that the probability of my heating time being less than t is equal to that expression I have there. Now the expression, I'm not going to look at that expression right now. What I want to highlight is this gives me the cumulative distribution function for heating times. So this is a big deal. And this is done using the cumulative distribution function of the Gaussian. Okay, so this gives us the probability distribution of heating times. One of the advantages of creating this axiomatic approach to brownian motion. Okay, now other properties of heating times. It can be proved that for every level, the probability that the heating time is less than or equal to a certain value t is equal to 1 as t goes to infinity. In other words, brownian motion will hit every possible level at some point. It may take a long time, but brownian motion will get everywhere. That's another way to state something that we already know, meaning that every point will eventually be hit by the process with probability 1. However, we're not going to prove it here, but it can be proved that the expectation of that time is equal to infinity. Okay, so bigger and bigger points will be reached later and later, and if you take the expectation of all those heating times, the expectation is infinity. So sometimes it could take a very long time. Every level is going to be hit, but the expected time is going to be infinite. There's another characteristic that we can obtain through this approach. Using the simplicity of brownian motion, which is the running maximum. The running maximum is the following. It's very intuitive, and it's something that we've already described also in a previous lecture, but now it's coming up in its formalized form. Imagine you run the following experiment. You flip coins in a sequence, okay? +1 is for heads, -1 is for tails. We have a pretty good idea. About where we will be after we flip thousands of millions of coins. We know that. That's given by a Gaussian distribution. Or equivalently, as we run that experiment where we were walking from the university to downtown in a random way, then we were able to calculate, based on my steps to the right and to the left, we were able to calculate how far from the center of town we will end up being. That's an experiment I will run. But imagine I ask you a different question now. I ask you, okay, so we know more or less where we will end up from the center of town, but how far will we have deviated in our walk to the center of town? How far would we have ever gone? Or if I flip my coins, how high would my balance be, or how low would my balance be in my path moving forward? That is a more complicated question. The simple question where I will end up, we know, because we know that this stochastic process is a Gaussian distribution at every point in time. So the distribution is given by a Gaussian distribution. But what if I tell you how far we would have gone? That we don't know. It seems that we could have, veered very far away only to come back. Or if I flip coins, maybe we went through a very, very large sequence of +1s, only to then come back to where we expect the distribution to be. The thing is that in the case of brownian motion, this is a number that we can also calculate, also using heating times. Okay, so if you run a game, you want to know what is the largest balance you will carry over time. Okay, which is a more difficult question than to know what balance you will have at a point in time. This is the largest balance you could have observed through time. So when we're dealing with brownian motion, what we want to do is we want to define the largest value observed between the beginning of time and today. What was the biggest value we would have observed? This is something that we can also calculate This, by the way, this is a very important quantity in asset management. I'm going to define it for you. I'm going to tell you. This is related to the probability of getting a margin call. Okay, I'm about to show you that. The maximum deviation from the origin we will exhibit in a Brownian path is obtained as follows. The probability distribution for this running maximum is exactly equal to the cumulative distribution function of the heating times. That's what we need to understand. Because both represent exactly the same event. If the running maximum at time t is bigger than x, that means that the heating time for x has already happened. Exactly the same. But if we know the probability distribution of the thing in the right, then we know the probability distribution of the thing in the left. Therefore, we have that. This is surprising. I was, when I first learned this, I was shocked because it seems that it gives you a very good insight about the history of motion. When we defined, this is unexpected. When we defined Brownian motion, we knew that at every point in time without a distribution. So I would not be surprised by anything that tells me information about where we will be. That I'm not surprised. But that I can tell you what would have happened in my path over there, I found that to be surprising. Of course, it's a consequence of the reflection principle. It's a consequence of the fact that we can calculate the probability distribution for heating times. It's a consequence of the fact that at the end of the day, Brownian motion is a Gaussian random variable moving over time. But still, I find this to be surprising. Okay, and I want to give you a simple application of this, which is the probability of a margin call, something that we've already discussed, but now it comes up naturally in this context. So imagine I have a certain portfolio with a certain PNL distribution with mean zero and standard deviation, whatever, sigma, right? And imagine I have a collateral, which is a number given to a certain number A. Say I have $1 million of collateral, and I have a portfolio that has a certain mean and a certain standard deviation. What's the probability that I get a margin call at a certain point in time? So a margin call is basically, it's an example of ruin. Means it's an example where my portfolio has exceeded losses in excess of A. That's what a margin call would be, right? So, by the way, it's not the same as to say that, at times, say in a month, I want to be hitting a margin call. Maybe I hit a margin call within a month. The probability of running out of money in a month, we already know it's a Gaussian distribution. But the probability of running out of money at some point within the month, that question is strictly about a process, not about a distribution. And this is one of the difficulties that these questions have. But in the case of Brownian motion, we know exactly what the answer to that question is. Okay. So to answer that, what I'm going to do is I'm going to answer the opposite question, which is what's the probability I do not get a margin call? Because the probability of not getting a margin call means that the probability of loss does not exceed my capital A, which is given by this distribution that we just presented earlier. Okay? So that gives me the probability of not getting a margin call. It's explicitly calculatable. In the context of a Brownian motion, of course, if I lose the Gaussianity, the Gaussian nature of my Brownian motion, this will not be the case. I'll have to look at a heating time of perhaps a more complicated distribution. Okay, so this goes to show how powerful Brownian motion is, all the things that we can do with it. And I want to end this first part of my lecture today by giving you some consequences of what we have built, things that we already know, but now we can go back and revise. Geometric Brownian motion is a specific type of Ito process where ds over s is equal to an Ito process of that type. Okay, so this is something which the thing on the right is something that we defined. It is the Brownian motion with the drift that we defined earlier. And if I multiply this by s, then I have my Stoch process. The Stoch process is something which we have used extensively in our analysis. And it has all the right characteristics. It preserves the limited liability characteristic of a company, doesn't become negative, prices change proportional to stock prices. Okay, so these are things that we already saw, and that's, now we're fully justified in our use of Brownian motion for that. Okay, so this is new. But now I want to I review here Eitor's lemma also. We have seen the difference between the normal and the logarithmic stock prices that we have also seen are related to the fact that the discretized version of the Ito process on the right is exactly the way we define returns of stocks on a given day. Okay, so again, these are things that we have seen, and logarithmic prices are related to standard prices by Ito's lemma, and again we have seen this, and all of these things have been built on the back of our definition of Brownian motion. Okay, so this ends the first part of my presentation today. We're going to take a 10-minute break, and after the 10-minute break, what I'm going to do is I'm going to look at other stochastic processes that we have not seen, and we're going to see the power of combining different stochastic processes with each other. Okay. So after doing the formal derivation of Brownian motion, which after all is something we've already worked with a lot, I want to now use this approach of formal frameworks to do the formal derivation of a new type of stochastic process that is new to us, at least new in this course. We have not used it before, and that's Poisson processes. So I start with a review of the Poisson distribution. I assume it's something that you have seen in probability. It refers to a random variable that has discrete outcomes as opposed to normal distributions, which give you real numbers as outcome. This gives you integers as outcome, positive integers or non-negative integers. So the outcome could be 0, 1, 2, 3, any number, any integer number. And they are parameterized with a real number, beta, which is going to refer to the mean. The probability distribution of each number occurring is given by this expression. The probability that I get outcome k is my parameter beta to the power k times the exponential of negative beta divided by k factorial. A few things to say. Again, I'm assuming that you've seen this, but I will tell you anyway as if you have not seen it. This is an interplay between the parameter beta and the outcome k. You see, as the number k becomes bigger and bigger, the factorial will win over everything. So that's why this probability for very large numbers k will go to 0, even if the number beta is big. The number, if beta is big to the power k is big, but divided by the factorial, eventually the factorial will win. And the role of the exponential is just to ensure that the sum of all of these terms add up to 1, so it's a probability space. Okay. B is at the same time the mean and the variance of this random variable. Now the intuition of this is if B is large, then b to the power k is going to win when k is larger. Of course, not so large so that the factorial wins. Okay, so basically in this struggle in this formula between beta to the power, there's a struggle in this formula between beta to the power k and k factorial. These are the two elements which are struggling with each other. If beta is large, then beta to the power k wins when k is larger. When k is small, the exponential term makes beta to the power k smaller. So this, what beta is large, what that means is that it makes the relevance of this term relevant when k is larger. Okay, so k has to become larger to win over beta to the power k. And at the same time, or similarly, when beta is small, the opposite happens, which is you don't want to raise beta to very large powers because it becomes very small. So lower k's are the ones that will matter. Because if beta is small and k is large, then beta to the power k will become smaller. And of course, the factorial of k will just kill everything, right? So the relevance or the size of these numbers is going to be the result of this struggle or this competition between beta and k. And the term exponential of minus beta is there only to ensure that the sum of all of these numbers equals 1. The sum of these numbers equals 1 because this is the Taylor expansion of the exponential function, so we know that e to the power 0 is 1. That's why the sum of all of these is 1. Okay, that's why it's a probability space. So let me just give you a graph. I have here the Poisson distribution for actually three different parameters. The first is for a parameter beta equals 1, and I can see that the biggest value is 1, and then it just keeps going down. This is for a beta equal to 5, and as promised, you see, it's actually around beta equals 5 that this distribution becomes largest. So the most likely event to happen when beta equals 5 is 5. And when beta equals 10, the most likely event to occur is actually event 10. So beta is not only the mean and the variance of this distribution, beta is also the most likely outcome of this Poisson distribution. Now, there's something interesting about the Poisson distribution, which I've tried to validate, and I've only validated partially. The Poisson distribution was discovered independently in different countries before there was Twitter at the end of the 19th century. And it was considered to be so important that it was a military secret for countries. They wanted to, they saw that this is very powerful. You will see why. We're going to be very powerful with this today. And it was discovered just before World War I, and it became a military secret of countries. And I think it was in the UK. One of the studies that they did to validate the relevance of this Poisson distribution was they had kept a record of the number of soldiers who had died from a horse kick. They needed to take a very unusual event, because the Poisson distribution works best when you have unusual events, when beta is low. And they saw that it fits this exponential distribution very well. A few years later, they had a chance to see that the distribution of bombs when Germany was bombing London also was very closely modeled by the Poisson distribution. So now it's in every book, and We'll talk about that openly, but for a while it was actually kept a military secret. It's a very important distribution, and we're going to see some examples of that today. But what I'm going to do is, before I go to the examples, I want to use this as a way to give a technical definition, just as I did for brownian motion. And you will see that there is a commonality now between brownian motion and Poisson processes in the way we define things. And by the way, this is going to be the way we're going to define stochastic processes tomorrow. So a Poisson process with intensity beta will be defined as a process with the following characteristics. It has an initial condition, which is 0. It has independent increments, in other words, the difference between two sets of observations are independent random variables, not Gaussian anymore, okay? In fact, they are Poisson distributions, so that the increments between two observations, are distributed like a Poisson distribution with intensity time lapsed times parameter beta, okay? Or mathematically speaking, the difference between the two distributions is a Poisson distribution with parameter beta times the time lapsed between t and s. Now, let's reflect on this. This is a completely different distribution from Poisson, but you see that it's written in exactly the same way. So now we can hypothesize, well, if the Poisson distribution is written, sorry, the Poisson process is written like this, and the Gaussian and the Brownian path is written in a similar way. Is there something to that? Can I or should I define stochastic processes like this? The answer is going to be yes. We'll see that tomorrow. So, propelled by the fact that both the Poisson process and the Brownian process are so similarly established, maybe this gives us the key to understand processes in general. And we will do that. This is the perspective we're going to be adopting tomorrow. Now, back to the intuition development. If I give you here two sample processes, and these have been generated by a computer, and there's one on the right and there's one on the left. They're all generated over 10 time steps, but the outcomes are different. In one case, they go from 0 to 10, and the other one go from 0 to 80. Can I ask you to use your intuition to tell me the parameter beta? Can you do a mental calibration of these processes? Tell me what beta is in the case of the right and in the case in the left. I want to ask you this because I want you to realize something important, intuitive, that will help us as we go along.
Is it 1?
One is the one on the left, right?
Yes.
And the one on the right?
I think they're the same.
You think they're the same?
Yes.
The pictures are misleading because you see the dimensions are different in both of them, right? In the first one, you can see that the slope is 1, and in the other one, the slope is 8.
Okay.
Right? So I apologize for that. I had no way of. But the slope is what gives us the parameter. Why? Because I'll remind you that the increment was distributed like a Poisson distribution with time lapsed times beta. So if the time lapse is 10 and we've reached 80, beta should be like 8, maybe 9 on the right. Whereas on the left, yeah, it's clearly 1. Okay? So Poisson distribution with high beta grows faster. and a Poisson distribution with lower beta grows more slowly. That's the intuition I want you to have.
Yeah.
Okay, and we can see that the key to understanding these graphs is in the different dimensions that I have. In fact, the dimensions of these graphs is what tells me what is what. All right. Now, the interest of Poisson processes, of course, they're interesting in their own right, and they help explain things such as dropping random things on a city. But the interest for us is that because they give me integer numbers, not real numbers, I can use these integer numbers with a certain intensity to select other random variables in different numbers. So this is what's called a compound Poisson process. So if I have a sequence of independent random variables, whatever they are, they could be Gaussian or non-Gaussian, or doesn't matter. I call them y. If I have a sequence of random variables y, and I call, assume they're independent, okay? If they're independent random variables y, then I can choose my Poisson process to also be independent of y, and then construct the compound Poisson process as the sum of these independent random variables y in a number which is equal to n, and n is given by the Poisson process. Okay, so this is, we've created a new process. A process is it's a new stochastic process. It's x sub t, and it's going to be changing over time. And at every point in time, what we do is we select randomly n sub t variables out of my collection of independent random variables y sub k. So as time goes by, n is going to grow. It's going to grow like beta times t. Okay, so I'm going to have, as time goes by, I'm going to get more and more of these random variables, and I'm going to add them up. That's what's called a compound Poisson process, and it's the composition of independent random variables, which, by the way, they could come from brownian motion if I look at the increments, for example. Okay, so this gives me almost limitless ability to construct a new class, an entirely new class of stochastic processes. See, at this point, I need to now defer to tomorrow, to next class, where I will be defining stochastic processes in its greatest generality. I'm just giving you now more and more examples so that tomorrow we're very well equipped when I create the formalization of all of this. Okay. So I have an example where compound Poisson processes are very important. This is how insurance companies work. So I have a model. I want to be able to model an insurance company with a compound Poisson process. And an insurance company, I'm going to assume it's a company that has policies out there, and then it receives an average of a certain number of claims per week. I'm going to pick a very precise number, 20, okay, but you can call it N. An insurance company receives claims per week, and each claim has a Gaussian distribution with mean mu and standard deviation sigma. That's an insurance company. I'm modeling an insurance company. The total claims, the total liabilities of an insurance company then become a compound Poisson process with intensity 20 per week. Okay, so the claim process per week of an insurance company is a compound Poisson process with intensity 20, because every week I'm going to get a number of claims that's going to grow as this Poisson process grows. So this is going to give me, so this is the exact model for an insurance company. This is just the claim side of an insurance company, or the liability side of an insurance company. If I model the asset size of an insurance company, that is different. The asset size is a portfolio, and I will use portfolio theory for that. But the liability side of an insurance company is a compound Poisson process, written like this. Great, so this is nice vocabulary. This is only explaining to me what an insurance company is. What can I do with it? So what I can do with it is I can create, I can measure this. And in this context, there is something called the Wahl's equation, or I guess Wald if you're German. The Wahl's equation, what it's going to do is it's going to allow me to calculate explicitly the value of the insurance company. In this case, the claims of the insurance company, or the value. It's going to allow me to calculate the expectation and the variance of my compound Poisson process. The compound Poisson process is something that we have explicit control over. I'm not going to prove this to you, I'm just going to tell you the expectation of the compound Poisson process is the expected number of claims times the expected size of its claim. Or, in the language of the compound Poisson process, is the expected value of my Poisson process times the expected value of my independent, identically distributed random variable. In other words, it's as if n is constant. If n was constant, the expectation of a sum of random variables is the sum of the random variables. So that is somehow to be expected. Now the variance is a bit more interesting because the variance will tell me the following. If n is fixed, so not a process, if n is fixed, what is the variance of the sum of independent random variables? The variance of the sum of independent random variables is going to be the sum of the random variables times the number of variables I have. So if n is fixed, in other words, if the variance is 0, then I recover the formula I already know, which is the sum of independent random variables is a random variable. Sorry, the sum of independent random variables. Sorry, the standard deviation of the sum of independent random variables, identically distributed, is n times the standard deviation of each one of them. And that's what I have here. That's if that is not a process, if it's a number. The nice thing here is that if it's a process, then the variance that results, of course, is going to increase its variance. The whole variance of my process, if n is not a constant, if n is a variable, a random variable, gets increased by that. Now, I have important things to say about this. So this is important because it tells me that uncertainty in the number of claims increases the variance of x. Increases the uncertainty, yes, but increases the variance. This is very cool because if I have an insurance business which is very predictable, that means the risk associated with that is going to be lower. There's no way getting out of that. That's always going to be there. The variance of its claim contributes to the variance of my business. There's no question about that. But the variability in the number of claims is going to increase the risk of my insurance company. There's more to this than just this, because how do insurance companies work? Insurance companies are based on diversification, which is if you can diversify, then you have a business. But typically diversification is in having a lot of claims that I can get. And that's true. The more insurance policies I sell, see the variance, so the risk is the square root of the variance, right? So if I have this, the square root of the variance, again, imagine that this is 0 for a minute. If this is 0, the risk of my insurance company, which is the square root of the variance, is the standard deviation of its claim, which is fixed. So this does not depend on why it's fixed, times the square root of the number of claims. That means that if you're diversified, your risk goes down. Why? Because the premium are linear. The premium of each insurance company is the individual premium times the number of claims I have. So this grows linearly, and this grows like the square root of n. That's why insurance companies exist. But they need to be big. They need to have a large collection of diversifiable claims. But what this says is that if the uncertainty I get is not only in the claims I get, but also in the number of claims that I get, then my risk goes up. In other words, an insurance company has two sources of risk. And that's what we learn from Paul's equation. Source of risk number one is this one, which I can handle by growing the business. Why? Because as I grow the business, my risk decreases like 1 over the inverse of the square root of the expectation of the claims. But then I have another one, which is here. That's another source of risk for my insurance company. And this is proportional to the standard deviation of the number of claims. So if I have a business, an insurance business, where the number of claims is very constant, the standard deviation of the number of claims I get is low, then that is less risky than otherwise. Let's find an application of that. Can you give me, can you think of an example where this thing, for insurance, where this thing is large and small? This is small in the car insurance business. The number of claims for car insurance is very low. Sorry, the variability of the number of claims is very low. Why? Because there's a lot of cars and they tend to have accidents more or less at the same time. Perhaps in places like Canada, that's not the case. We tend to have an increase of the number of accidents when there's snow. So snow is a source of risk that makes my risk go from small to large. And therefore, because it increases that, right? But one area where definitely you have a large variability in the number of claims is in home insurance. In particular, if you're doing business in places like Florida, where a hurricane hits and then suddenly half of the homes are filing claims. That means that the variability here is very large. By the way, this is one of the reasons why insurance companies love car insurance. And one of the reasons why they don't like home insurance. Home insurance tends to be more expensive than car insurance, although the number of claims is less. And the reason is this first part of the equation. So this is just a mathematical expression, but there's a lot we can derive from it. Okay, I just give you an example. Okay. I hope that's clear. I don't know. It's I find this to be very interesting.
Yeah, very clear.
Yeah, it gives us a very good understanding of the insurance sector. So let's go back to my insurance claim and let's just do a calculation. According to my number in my previous example, I have that the expected value of my claims is going to be 20 times mu. Mu is the size of each individual claim, 20 per week. So that's going to be on a weekly basis. That's what I expect, and the variance of that is going to be 20 times sigma squared, as I expected, but then also mu squared. The thing is that the variance of n is equal to the intensity. Okay, I mentioned that at the beginning, and now I can use that. And the size of each claim, mu, now enters into the additional risk that I pick up when I do insurance policies with a variable number of claims. Okay. So the total weekly claims has a mean of 20 mu and a standard deviation of the square root of that. But the important part is that is this increase here. That's the important part for me, how the risk of the insurance company grows because of the uncertainty in the number of claims. Okay, let me now continue. I think we found this new strength in our ability to understand stochastic processes. And I'm going to go to now a stochastic process of a different type. I have this one here, which is very important in finance. It's called the Ornstein-Uhlenbeck process, oftentimes called also the mean reverting process. It's written like that. I'll make some statements here. The process refers or is modeled by a variable x. X gives me a number, the level of something. I should tell you that this has an application to interest rates. So if x is an interest rate, this model has been used to model interest rates. So the change that the interest rate will have at a point in time, I call it x, is on the one hand, of course, has white noise, sigma times dw. So this is the Brownian noise that we have, which is you flip a random coin, goes up and down, right? That's sigma times dwt. We've seen that before. But look at the drift. The drift is something new. We haven't seen it before. The drift is not just mu times x. If it was mu times x, that means that just interest rates would just keep on growing and growing and growing over time, but they don't do that. They go up and then they go down. And this is a process that governs that. It governs how we go up and down because there's two parameters here. There's mu, which is the long-term mean, and then is alpha. Alpha is the mean reversion parameter. Let me explain to you how this works. This is a new stochastic process. So it uses a long-term mean. So for example, in interest rates, you say, well, interest rates are on average, 3% over time. Those, if they're lower than 3, they go to 3. If they're bigger than they come down to 3. So it's the long range mean. You start with that, mu. And then the key to understanding this process is in the intensity of the mean reversion term. Because if, and then of course the randomness, if you look at if you look at the sign of that, that tells you that if you are x is the interest rate. So if x is below the long range mean, then mu minus x is positive. So the process tends to go up because the drift is positive. And if you are above the long range mean, that term is negative. So the process likes to go down. Okay, so this drift is not like the one we saw earlier today. This drift is one that makes the process go up when it's below the long range mean and go down when it's above the long range mean. And the intensity at which it does that, or the velocity that uses for that, is given by this parameter alpha. Okay, when alpha is large, it tends to revert very quickly, and if alpha is low, it tends to not revert very quickly. This is a model. It's used in finance. It's used in many other things too, by the way. Okay, but it's one what is there, and it's a variant of the Brownian motion, and it's another of the examples that we will use tomorrow to formalize what stochastic processes are. Okay, the most famous application of this is the Vasicek model for interest rate. It was introduced by Oldfish Vasicek. It's a model for the spot rate of interest rates, and it's written exactly like that. That's exactly how it works. So mu is the long-term mean for the interest rates, and alpha is the mean reversion parameter, and sigma is the white noise. When mu is allowed to depend over time, this is a model that was attributed to Hall and White, who not only did that, they also came up with an efficient method to calculate or to implement this model with trinomial trees. That is an important part of finance. You may see that in some courses in this program. Okay. When both mu and alpha are time dependent, the model is attributed to Vasicek. So this is something, Hall and White has become more famous for some reason than Vasicek, but they've all been working on this model independently of each other. Something interesting is that this model allows for negative interest rates because, as we saw, we'll have to do the version of heating times that we saw earlier today for this, and the result is very similar, which is the probability of heating anything is 1, as we saw earlier in the lecture today. This is the same. So in particular, the probability that rates are negative is not 0. Maybe low, but it's not 0. This is one of the characteristics of this that practitioners that use this in practice, they need to know. Okay, you just know that. There are variants of it that allows for interest rates to not become negative. And the one that I want to show you here is this, which is very interesting because it has some things to say. This is again another stochastic process. It preserves the mean reverting part. But now look at the stochastic part. The stochastic part has been modified. It's different now. It's not just sigma dw. Is sigma times the square root of the interest rate times dw. Now this is a very beautiful model because this model prevents rates from becoming negative. Let's look at that intuitively. For a model to become, of course, rates are positive now, okay? So they could become negative in the future. For a rate to become negative in the future, what will have to happen? I'm looking at intuition, only intuition. I'll have to develop the heating times analog of what I did earlier, but intuitively, if I look at this model, what I have is a mean reverting term with a drift, which certainly is not going to drive interest rates to 0. That likes to drive rates to mu, and mu is positive. Okay, so if rates are low, that's term is going to try to push them up. So that's not going to be a source of negativity for interest rates. It never is. It's the other term that could just randomly walk its way into a negative interest rate. It could happen with the Vasicek model, as we saw there, because Brownian motion can go anywhere. We saw that earlier. The heating time is finite for any value that you pick. But in this case, what happens is that as R becomes lower, the noise, the white noise, the volatility of my Brownian motion vanishes. So there is some argument to be said that if the volatility vanishes, then maybe rates would just run out of white noise power to make them negative, and then the mean reversion will win. And this intuition is right. This is actually something that can be proved mathematically. I'm not going to do that today, but again, in the formalism we'll develop tomorrow, that gives us the key to be able to do things like that. Like, for example, proof that this will not approach 0. Interest rate will not become negative as a result of that. There is an aspect, or this can be generalized to a whole new a body of knowledge, which is the theory of stochastic differential equations, of which this is one. And we can prove that this is the case. This is not something I'm going to prove here for you, but I just want to highlight that this is something which is true. And one of the nice things that one of the wins that we can do when we try to do mathematical modeling in finance. There is a result which is a bit stronger than that. It actually shows that any process of this type where I take the volatility term sigma and I multiply by a power of r, that will not become negative as long as the power is a half or bigger. See, if it's bigger than a half, suddenly the white noise, the volatility is going to vanish as the rates become negative faster and faster and faster, the higher the power is. If the power is very low, then the white noise could win, and in fact, it does win when the power is less than a half. Okay. So that's another statement that we can get here. Now, another thing that we could do, another stochastic process we could develop out of all of these formalism we're developing today is what's called brownian motion with jumps. Brownian motion with jumps refers to the following. It's the addition of a brownian motion with a certain drift and volatility, as we saw earlier today in the first part of the lecture today, and a Poisson process with a certain intensity. Okay? When you add the two, what you have is you have a brownian path that every once in a while gets hit by a jump. Okay, this has been used also in finance by several authors to understand why every once in a while stock prices, they exhibit what is called the large tail events. So events that cannot be explained by the Gaussian distribution. So what they do is they just add a Poisson process to it, and then the result can explain why on occasions you just have a little kick given to the stock prices and then it goes up or down. Okay, because you can model the end with any sign that you like. So that's another example of another collection of processes that we can do. And yet another one that we have here is a Heston model, which is now belongs to a group of processes which are vector processes, not scalar processes. It's another one. A Heston model is a vector process which is of the form as follows. I have on the one hand the good old stock process with its mu and its sigma and its brownian motion, but then it has another one that covers the volatility, which is not constant in this case. So the volatility is going to be a stochastic process in itself, and we make it be a Cox-Ingersoll-Ross process. In this case, not applied to interest rates, applied to the volatility, which I need to keep positive. That's why I picked the Cox-Ingersoll-Ross process for that. So if the volatility follows a mean reverting process with a volatility term that scales like the 1/2 power, like the square root of the volatility, then I have guarantees that this volatility process does not become negative, which I need. I need volatility to be positive always. And then I feed that volatility term into my stock process above. This is a very popular stochastic process. We assume that both brownian motions are independent, although they could be correlated if you want to. There's no need for us, certainly not today, to assume that. This is very popular because it also allows to use or to model. It allows the modeling of markets where on occasions you have volatility clustering. For example, we discussed a few days ago the events of October 1987 when the S&P 500 dropped 25% in one day. How can you model an event like that? With brownian motion, that would just never happen. You're never going to have that. However, if you model stocks with a Heston model like that and appropriate parameters, you could have the ability to model situations like that. Perhaps not as extreme as 25% in one day, but certainly big. And this is what this Heston model has been designed to do. So as you can see, these the ubiquity of stochastic processes of different types here, there, and everywhere is the key to the modeling. In our case, in finance, but of course in other processes in nature, it just makes the mathematics that we can work with very strong, and then it allows for, in this case, for example, it allows for what's called volatility smile, something that I did not have a chance to explain, or actually not even the interest for this course. But again, this goes to show how rich all of this can be. Okay, and as I mentioned, the square root sign ensures that this is going to be positive. Now, all of this that I'm talking to you about is nice and gives us, makes us very powerful in our ability to model what things are out there. With that comes the risk that we have so many models in front of us that we can run into model risk considerations. I mentioned at the beginning of today's lecture how model risk, when we're doing modeling, is the equivalent of data overfitting when you're doing data science. Okay? So it's something that we need to be aware of. Because of that, the more complex the models, the more difficult it will be to calibrate each of those models. And practitioners, they tend to prefer simplicity over complexity because that is how we minimize the risk that exists in this category, which is model risk. Okay, parsimonious models are the ones who depend on little data and therefore do not overfit the data so easily. This is related to the notion that we derived of tree pruning when we were talking about random forests a few days ago. Okay, and parsimonious models they also are they have bigger explanatory powers because you have less parameters available to you. And the maxim that people use this model which is as simple as possible but not simpler. Okay, now what I have now is it's 9. I have some problems to do with you, but maybe what we do is let's take a 10-minute break. Yeah, let's take a 10-minute break. I want to walk you very quickly through these examples that I have here, highlighting what is important to learn. But then I will end today with, I think it's the natural continuation of what I did which is how to do Montecarlo methods, what they, when they work and what they don't. And then tomorrow I will do the one thing that has to be in my course, which is the framework for the rigorous definition of probability spaces and stochastic processes. I'm less concerned about your understanding of that now, because we have seen everything that we can do with them and all the practical applications. But then I will end with the formal derivation. I'll do that tomorrow. Okay, so now I'm going to do some examples, mostly to fix the ideas that we have here. I have, for example, this exercise. I'm just going to go through this quickly. You can do them more slowly on your own. I'll have all of these notes uploaded to the website, so people who are watching the videos can do this on their own. So what's the probability that my brownian motion is negative 4 times equals 2? It's very simple. We just observe that the brownian motion is a Gaussian random variable with mean 0 and variance square root of 2 at time 2, so it's a half. More difficult than that is, let's calculate the probability that a brownian motion is negative both at times 1 and 2. Okay, and what's important to note here is that it is a common mistake is to think that brownian motion at time 1 and at time 2 are independent, and therefore one would get that, but that's actually not true, because it is not true that brownian motion as a process at time 1 and at time 2 are independent of each other. That's not true. What is true is that brownian motion at time 2 minus time 1 and at time 1 minus time 0, which is now, those are independent. So this is what's independent, not the previous one. So we have to do this a little bit differently, because now we do have the Brownian motion value at time 2 as the sum of two independent random variables, which is the increments between 0 and 1 and 1 and 2. And they're actually independent and identically distributed, but they are independent. So the solution to that is the probability that my Brownian motion is negative at time 1 and the probability that my Brownian motion is negative at time 1 plus time 1 person 2 is the same as the probability that the value at time 1 is negative and the value at time 1 is less than or equal than the negative of the value at time 1. Conditional on W1 being equal to X times the probability density of that. So the result of that is what you have here. It's I can read it to you, but it's better if you just walk through it yourself. The answer is 3/8. Okay, start. Okay. Now, how do we calibrate Brownian motion? The way to calibrate, and this is related to Montecarlo theory, how do we calibrate Brownian motion? The way to calibrate Brownian motion is as follows. If I have given observations which arise from Brownian motion with drift, we can calibrate the parameters mu and sigma as follows. The mu can be obtained by taking the averages of all the possible observations, the increments of the observations divided by the times. We know that this number should be mu on average, so we just take the average of that. And to calibrate the standard deviation, what we do is we normalize each of the observations that we have with a mu that we have calibrated, and the square root of time, which is supposed to be the variance of that variable, and the standard deviation of that will be the standard deviation of the Brownian motion. So this is how we calibrate the Brownian motion. This is, I'm going to, as I mentioned, I'm going to close today's lecture with a more in-depth description of Montecarlo, both in terms of how we calibrate and how we generate scenarios. This Montecarlo is really a combination of both things. This shows us how we can know, given a sample, which Brownian motion it's coming from. Okay? So the sampling problem that Montecarlo addresses, and the sampling problem we just touched on now, that I'm going to get more in depth with now, is a dual problem. On the one hand, given a distribution, we want to be able to generate data that is consistent with that distribution. And the other is, given a distribution, I want to know what distribution, given a sample, I want to know what distribution that's coming from. So we just saw that in the case of Brownian motion. We saw how to go from X to rho. What I want to do is I want to talk about how to go from rho to X, the generation part, okay, which is it's actually more complex. It's more difficult. And one of the reasons it's more difficult is because of the concept of randomness. I am not going to give you, long conversation on randomness, but I will say that mathematically, to generate random numbers is an impossible task, because nothing is really random. You can generate an algorithm, and by the fact that you use an algorithm, you're going to end up with something which is not random. It's just the result of an algorithm. However, the philosophical discussion is not interesting. It turns out that for most applications, we can generate numbers which are better than random. So let me explain that. Better than random. Okay, random is perhaps impossible, but we'll understand what it is, and we build mathematical theories with that. When you have to do something practical, better than random is going to be better. And we're going to call it pseudo-random. The word is pseudo-random, but I like to call it better than random, and you will see why. Okay. And for that, I want to adopt a different target. I want to say, imagine I have a uniform distribution on 0, 1, and I want to have a sample which is like a uniform distribution in 0, 1. How can I do that? And I'm going to propose to use this method. This is a method which is widely used in computers, but I have some very important considerations to make with this method. The method is this. I take a number S naught, it doesn't matter what it is, it could be 0, it could be any number that you pick, to ensure that the result of this algorithm is always different when you run it on different computers at different times. Typically, S naught is something related to the time of day. The time of day in absolute terms, not the time of day today, the time of day, so that S naught will always be different every time you run the algorithm. And then what you do is, to that number, you add n times the n times, and to pick an irrational number, like the square root of 2, for example, and then you add, you multiply that by integers, and you take the fractional part of everything that comes up. So this will give you a number which is between 0 and 1. It's not random, because it's the result of an algorithm, and but it does have the properties that it is between 0 and 1. Of course, this is predicated on the fact that alpha is an irrational number. Irrational numbers cannot be really put into a computer, because computer will give us a finite digit representation of them. However, it is known that if you pick certain numbers, like these ones, the golden ratio, the square root of 2, or others, the result is going to be very, very good, very close what the computer will do to what theoretically you would find. And the reason is that these numbers are numbers which we know are very badly approximated by rational numbers. So you can generate millions and millions of random numbers, and they will look like what they should be. Okay. Now these numbers are not random; they are pseudo-random, and but we're still going to use them to address this important problem. The important problem is that this is the Monte Carlo problem. Given a data distribution with a probability rho, how do I produce a sample that follows that distribution? That's the problem, which is, so I just did it for the uniform distribution. I didn't tell you why. That's coming. But we can take this question and make it more general and explain why or how, if I give you an arbitrary distribution, not necessarily uniform, how can you generate numbers which are reproduced as a function? And the answer is very simple. The answer is the basis of Sklar's theorem. It says, if F is the cumulative density corresponding to the probability density rho, so the antiderivative, okay, and I generate a uniform distributed sample, then F inverse of that uniform distributed sample is distributed like rho. That's the theorem. Let me explain that in graphical terms. We've seen this many times. I've seen this graph many times now in different contexts. It's coming up once again, because in this context where it says that if what I have on the y-axis are uniform numbers on 0, 1, where I get mapped into the x-axis, F inverse xn is distributed just like F or like rho, up to you if you want to look at the density as the derivative of the cumulative distribution function. So this is Sklar's theorem, and this is the key for sampling, because with this, these are two are related, because with this I can do sampling of any distribution in dimension 1. And the key to that is to do the sampling not with not with random numbers, but with pseudo-random numbers, which work better. So let me show you how that's done. I'm going to show you the one-dimensional Monte Carlo algorithm. I want to do it in 1 dimensions, then I'll do it in high dimensions in the case of Gaussians, and then I'll tell you how it's done in the case of non-Gaussians, which is where the real party begins. Things are really difficult here. But in the case of a one-dimensional Monte Carlo, things are quite easy, because if I can generate random numbers in dimension on the unit interval, and we could do that with the algorithm I gave you earlier with the fractional part, then that gives me, through mapping through F inverse, gives me F distributed random numbers on the real line. So if F is, for example, the cumulative function of the Gaussian, then when you map them back through the cumulative function of the Gaussian, you have normally distributed random variables. Done. Very simple. Very simple. Okay. You can extend this to higher dimensions in exactly the same way. You take a seed number, doesn't matter what it is, and then you multiply by an integer vector, a vector that contains irrational numbers which are irrationally independent in each of their components. For example, the golden ratio on the first one, the square root of 2 on the second, the square root of 3 on the fourth, and this and that. Okay. The square root of 5 won't work because it's already in the golden ratio, so you have to go to the square root of something else, 7. So, then this gives you the ability to generate pseudo-random numbers in higher dimensions. And all of these are consequences of number theory. Now, what is perhaps interesting to point out is that when I do things like that, what I end up generating is random numbers on a hypercube. That's what that does for me. And again, this is the result of a very nice algorithm. And again, these are not random. They are better than random. I'll explain why. Okay, they are better than random. But there's a problem here, which is that the higher the dimension, the more difficult these things become. But there's one case in which these things work pretty well, and that's in the case of Gaussian distributions. So Gaussian distributions have the characteristic that the variance covariance matrix has all of the benefits of capturing the dependent structure. For distributions which are not Gaussian, then we have to resort to something which are copyless, which I will explain in a few minutes. And that's the way to do it. But this is far, far more complicated, okay? Far, far more complicated. So let me focus on multivariate distributions for the Gaussian first, okay? And then I'll show you how we do this in the non-Gaussian world. So for Gaussians, I have the cumulative distribution function of higher dimensions is given by this definition. And we have seen this before. This is the Gaussian density, which we've also seen this before, although we don't need any of this for today. We don't need any of this. I'm going to start with the formula we have seen many times now, which is the expression for the Gaussian distribution with the exponential and the variance covariance matrix. This is the multivariate Gaussian distribution. And then if I am given any distribution which happens to be uncorrelated in the marginals, like we did Brownian motion earlier today, then the covariance matrix is diagonal, and the Gaussian distribution is the product of one-dimensional Gaussian distributions. So my high-dimensional problem disappears because my multivariate Gaussian distribution is the product of single-dimension Gaussian distributions. So dimension is always the curse that you have when you do Montecarlo. In the case of the Gaussian with uncorrelated marginals, at least one aspect of the calculation is done. Okay. Now, the problem now boils down to doing Montecarlo for a Gaussian dimension in dimension 1. We'll go back to dimension 1. How can we do then Gaussian distributions with arbitrary covariance matrices? Through diagonalization, at least in principle. This is not computationally efficient, but in theory, it would work. If I take my variance covariance matrix and I diagonalize my variance covariance matrix to an orthogonal matrix, then I go back from any arbitrary variance covariance matrix to one which is diagonal. There's a better method than that, which is to, instead of using the diagonalization that you know, is to use something called the Cholesky decomposition, which is a technique from computational data science, computational numerical methods. And the Cholesky decomposition has the characteristic that the variance covariance matrix is the product of the matrix times its transpose. It is fantastic, very, very useful. And this allows me to do the following. If I have, I'm going to do the sampling part. If I have a multivariate Gaussian with an arbitrary n times n variance covariance matrix with a certain data set, then if the data set is multiplied by the inverse of the Cholesky decomposition, then what I have is Gaussian 0, 1. It's very simple linear algebra, because if we calculate the variance covariance matrix of this H inverse X with itself, what I get is I get variance covariance matrix times H squared inverse, which is the identity. So that's why. Okay. So this, what this means, this signifies that I can do the sampling of multivariate Gaussians through a very simple change of variables. This is the change of variables. If I start with my original multivariate Gaussian variable x, and I subtract mu, because subtracting mu is always easy, and if I multiply that by the inverse Cholesky decomposition, Cholesky matrix, then the result y is distributed, as I show you here. I don't really want to go through all of this calculation. This is to show you that the sampling of my variance, the sampling of my, to show you that the sampling of my Gaussian distribution is the same as the sampling of a one-dimensional distribution or a circular Gaussian distribution after the change of variables y. Okay, so instead of sampling x, which is hard, I sample y, which are related through a linear transformation. This is the key to understanding how we do sampling for Gaussians in high dimensions. And then this turns into the following algorithm. This is the n-dimensional Gaussian Monte-Carlo algorithm, where we put all of these things together. It all starts with how I started my lecture today, which is in one dimension, I can do that. I can generate numbers which are distributed according to Gaussian or whatever you want by mapping them through the F inverse. Okay. Now, you do this for every marginal, you do this. So for every marginal, you generate your components in this way. You use these to put them all together to create a multidimensional vector with independent components. You just put them one after the other, it doesn't matter, just line them up. And then you multiply this by the Cholesky decomposition, which you've calculated separately. And then the result will be a random Gaussian vectors with covariance matrix. This algorithm will give you exactly what we are looking for. That's how you do Gaussian Monte Carlo. That's how you do Gaussian Monte Carlo. Now, before I tell you how you do non-Gaussian Monte Carlo, let me make a comment. And this is a comment, you already know this, I suspect, but I'll make the comment anyway, which is, I told you that this, as you can see, everything boils down to doing sampling in dimension one, in the unit interval, actually. And I said earlier that to do sampling in the unit interval, I use this fractional part algorithm. And I told you that this is better than random. You cannot have random, but this is better than random. Let me tell you why it's better than random. And this goes back to something that everybody has studied at some point in their lives, but maybe they haven't told you the full consequences of that. Do you remember the birthday problem? The birthday problem, which I believe we have discussed in previous lectures, but now it's going to come up in its full glory. The birthday problem is the following. If you take 23 people in a room and you ask, what's your birthday? What's your birthday? What's your birthday? And then you collect all of the birthdays of everybody. You will see that there's a very, very high probability, it's like 95% chance that 2 of those 23 people have the birthday on the same day. That looks shocking because there's 365 days in the year with about 10% of the people, less than 10% of the people, than the number of days, I have the probability that 2 of them will have the same birthday on a given day. Once you do the probability analysis of that, you see that it's not shocking, it's actually a fact. And the reason is that, you may have seen that, it's a very well-known problem in probability. And the way it works is that if you try to calculate the probability that everybody avoids everybody else's birthday, it turns out that the connections between everybody, 23 people squared, is like 400 and something. If all of those connections have to be spread out in the year so that they don't touch each other, the probability of that is very low. And that's why the birthday problem is there. That's why the probability that a small number of people gives rise to a high probability of coincidences. By the way, this is the mathematical explanation why coincidences occur. Coincidences are very, very common. You cannot predict which coincidence will happen, but the coincidence happening has a very high probability. And this is the reason why. Now, there's a way to express this, which is that randomness favors clustering. That's what the birthday problem shows to us. And where that's the way randomness works, randomness favors clusterings and coincidences are very likely. That's very bad for sampling, because if I want to do sampling and I have a lot of clustering, that means I'm going to be oversampling some parts of my space and undersampling others. We don't like that. For most applications where sampling is needed, we don't want that. If I'm generating future scenarios, for example, and I sample in a random way, there are many scenarios, there are many areas, many market conditions that I'm going to ignore. That is just a consequence of clustering. So what if I could do sampling without clustering? That's called pseudo sampling. That's what this algorithm I showed you does. It's not something I'm going to show you here, but it actually does that. There is a very nice theory of it's called the low discrepancy theory for sequences and this and that, and it's based on that. So the birthday problem that you have seen in your probability course at some point has a very important consequence, which is that clustering is inconvenient and common when you're doing sampling. If you don't want clustering, then use pseudo-random numbers, or, as I said, better than random numbers. Okay. Now, this doesn't affect anything that I'm telling you here. The algorithm that you have in front of your eyes is the same, but when it comes to the generation of uniform random numbers on 0, 1, if instead of uniform they are pseudo-uniform, it's better. Your sampling for your Gaussian variable will be better in most applications. Credit matrix, for example, we saw we had to do sampling, better do it like that. If you're going to generate scenarios for example, risk matrix, you do it like that. Every time you have to do sampling, you do it like that. Okay, something which that is how that works. And I think now I have my Gaussian discussion complete. But let me finish by telling you how you can do sampling in non-Gaussian environments. Because if the environment is non-Gaussian, then we lose a tremendous property, which is that the dependent structure is given by the variance-covariance matrix. A matrix is a very simple object. And if the dependent structure between my variables is given by a matrix, then I'm in good shape. And as you saw that, I generate numbers, I multiply by a matrix, and I'm done. In a non-Gaussian world, you cannot do that. Things are much more complicated. And I'm not going to give you this discussion in its full. That's not the intent. I just want you to have a notion about this. But the whole thing starts the same way I started my Montecarlo discussion, which is that if I have a certain multivariate probability distribution, then the cumulative distribution function, defined as you have on the screen, okay, it's the cumulative distribution function done piece by piece, marginal by marginal, is going to be the key object that we study. If my distribution is uniformly distributed, then my values are between 0 and 1. So this is a map that goes from the unit cube into the unit interval in the case of uniform distributions. In the case of Gaussian distributions, it will be a map that goes from the real line into the unit interval. And if you pick any other distribution, non-Gaussian, with any dependent structure, it will also be a map between the n-dimensional Euclidean space and the unit interval 0, 1. Okay, so that's how cumulative distribution functions work in high dimensions. Now, Sklar's theorem in this context says that if you have your distribution, your cumulative distribution, and you take the inverse mapping, where the one that you have on the screen. So you take the inverse mapping with each of the marginals of your distribution, the result that you get is marginally uniformly distributed, which means that the marginals of this distribution are uniformly distributed. It's the same Sklar's theorem that we said at the beginning. It's just we apply this one marginal at a time, right? If you have a certain distribution and you map it with the inverse cumulative distribution function, the result is a uniform distribution. So this vector that we have in front of us here, f1 inverse x1, fn inverse xn, that is a vector which is its marginals are uniformly distributed. Its marginals. But how about the dependent structure? The dependent structure could be anything. We don't know what it is. We don't know what it is. But this will be a map between the unit cube and 0, 1, as we explained earlier. What map is that? Well, we don't know. No one knows. But what we know is that this map explains the dependent structure of that distribution. And this is what's called the copula. This function between the unit hypercube and the unit interval is the copula, and it defines the dependent structure. So if I know what this copula is, if I know what this function is, then I can do something just as before. Because this copula has the same role as the Cholesky decomposition. I can do sampling in each of the marginals because I know the cumulative distribution function of each of the marginals. I can do sampling there. Then I use the copula to put them all together. But how do you do that if you don't know what the copulas are? Okay, so what people do is they resolve it like that. There is a brochure of copulas. There's a Gaussian copula, a student T copula, a Campbell copula, a Clayton copula, Frank copula. So I say, which copula do you want? Pick one and use that. That's how this is resolved. The Gaussian copula is the most popular. By the way, the result is not a Gaussian distribution, okay? But it's the most popular one. Everybody uses that because it has very well understood properties. I'm not going to walk you through them and what they are. That's not the point of that. That requires perhaps a full course. But this is the way you can generalize what we showed earlier for our Gaussian distribution with a nice matrix to non-Gaussian distributions without a matrix, but with a copula instead. Okay. This became very, very sadly famous in the year 2008 when the financial markets, you know what happened to them, the Great Recession. And around that time, there was, you probably know that the credit default swaps and credit CDOs, credit default obligations, were big characters in this. Someone had published a paper that prices CDOs with the Gaussian copula. And for some reason, some newspapers got a hold of that and they decided to blame the financial crisis on the Gaussian copula. And David Lee, who was the one who wrote the paper, that's total nonsense. But this is perhaps the one time that copulas made it into the mainstream media. People were talking about copulas, about this, in the mainstream media. It was very interesting to watch. So I have a newspaper article that I can share with you if you're interested. I like to tell my students, go through the newspaper article and just highlight everything which is wrong with it. It's a very interesting exercise. But anyway, I think today I will leave it at this. I see if there are any questions. We did a very good coverage of all of these things. I hope I showed you the power of math because we're going to need it for tomorrow. Tomorrow I have to do, I'll try to make it not boring, but I want to do the formal setup that we need so that everything we have talked about here has a rigorous foundation. Okay? Because it's the only way, if you ever do something sophisticated, it's the only way to make sure that you're not blindsided by some fact. You need to know what the mathematical construction is.